important notion called the completeness role in contraction map, and we saw some situation in matrix theory where this we actually use. So that completeness is one important aspect of metric space. Those metric spaces which are complete have certain nice structure, and limiting processes are very well valid there. We can do nice limiting processes. Today I am going to introduce another important notion in metric spaces called separability. Okay, so that's the goal for today. This is essential from the actually from the point of view of, in a sense, trying to get some sampling set inside a metric space. In general, in a vector space, we look at a basis. By looking at what happens to the basis, we can basically tell what happens to all linear things that happens in the vector space. Analogously, in separability, we look at essentially a sampling set, and then by looking at what happens there, we can tell about what happens to all continuous things. Okay, so that's with respect to linearity and with respect to continuity. And as in vector spaces, we would like our sampling set to be as small as possible. Okay, and that's what we are going to do. So first we will introduce the notion of, so this will be our, from now all over, whenever I write X row, it means a metric space. Okay, so that I will not go on writing it. And everything that start defining things in metric space are motivated by what happens with the real numbers. These are our basic things. Okay, so therefore real analysis is one of the most important things. So let's look at the usual metric space, the real numbers with the usual metric, namely rho xy is equal to mod x minus. Now we have a set here. If you look at now Q, the set of rational numbers, the set of rational numbers is a subset of R, and it has the following property: given any x, give me any real number x and give any error, we can approximate this x by a rational number within that error. So there exists a Q which will of course depend on x and epsilon. To be very precise, I must write like that. It will depend on what number I am approximating and within what error I am approximating. There exists a Q x epsilon which is a rational number such that the error, if you take the difference or the error between x and q, that will be less than epsilon. Okay. This is the intrinsic property of the real numbers that comes from the way the real numbers are created. They are themselves created or approximating through rational numbers. Okay. So therefore, given any real number, we can approximate it within any accuracy we want by a rational number. Okay. In fact, if you are a computing man, you don't use anything other than rational numbers. I used to have a friend in computer science department several years ago, and he later moved to Jawaharlal Nehru University, JNU. Maybe some of you know him. His name Nambiar. Later moved to US somewhere. Okay. He used to always argue with me that I don't need your irrational numbers. I don't need your intervals. All I need are the rational numbers. Of course, then I used to always confront him with the Turing's halting problem, the continuum hypothesis, and then where do you end up with if you had only rational numbers? Okay, Turing himself would have been wrong, and computing itself will have different meaning, and so on and so forth. Okay, so the real numbers have their legitimate place. Just because you don't see something doesn't mean it doesn't exist. That's the problem with their science faces a stumbling like Gödel's incompleteness theorems, Turing's halting problem. All these are, we don't know what. It doesn't mean that it doesn't happen, or it doesn't mean that it happens also. We are not able to decide either way, and we'll never be able to decide either way. Okay, so now given any real number, approximate that real number within any accuracy by a rational number. We will now generalize this idea before. So what we mean by this is that basically within any accuracy the rational numbers act as a good sampling set for the real number. That's all. If you have located or studied real rational numbers, you have very close to many of the real number properties. Okay, so that's essentially what happens in continuity. Right. So we now generalize this. We will now take in place of the real numbers a metric space. Now in place of Q, a subset of X, a subset, I will call it as D of X. So the role of real numbers now changes to abstract metric space. The role of D is Q is replaced by an abstract subset of X, is said to be I will leave some space here and then write dense in X row if that property holds. If, what does that mean? Give me any real number. In place of that I should say give me any element of X and give me any error. Then I can approximate it by an element in D within that error. So if for every X in X and for every epsilon positive there exists a dxe epsilon in D such that now this modulus has to be replaced by the distance rho of X dx epsilon is less than epsilon. Then we call it a dense set. I will only write dense set, but I will usually it should be written everywhere dense set, because you can go and pick X anywhere in that space and still you are able to do it. So everywhere you go in the metric space you are able to do this approximation, because later we will see a notion called nowhere dense set, okay, and so on and so forth, okay, and which is another fantastic and most important notion in metric spaces and topological spaces. So now we have this notion of a dense set. Let's look at it in various languages. This means every element X in X can be approximated within any error epsilon positive by a given by an element of D. That is what it means. Okay, in words we should understand what this means. Mathematically we will write like this. Let us also write it in a different format. This means the following. This also means the following. I write it in various terms. In each interpretation we will use some time. Suppose I look at any open ball of radius r with any center x. Therefore, in any Prx, of course, where x is in x and r is positive, any open ball with center some point in the metric space and some given radius, there will be a fellow of D sitting inside, because now I can approximate x with a distance r, so therefore there should be a fellow there. There must be a D belonging to D such that D belongs to Brx. What does this mean? That is, every open ball must contain at least one point of D, or the intersection of any open ball with D will be non-empty. So that is, for every x in x, for every r greater than 0, Brx intersected with D is non-empty. You can also say that. Okay. So, this is what denseness means. For every point in the space and for every possible radius, the open ball centered at x and that radius will intersect D. Okay. So, what does it mean to say that it is not dense? What is the negation statement? There must be computer science students here. Are there? Are there any computer science department students? Yes. Now you must all be experts in logic. Seems to be a very illogical hypothesis, is it? Okay. So logic, what is the negation of this statement then? What is the negation of for every? There exists. So not D, not dense, means the following. For every x something happens. The negation of it is at least one x it will not happen. Okay, there exists an x in x, and for every r positive something happens. So some r it will fail, and there exists r greater than 0 such that this happens. So this should not happen. So Brx intersection D is equal to empty. Right? So there is at least one small open ball which is free from the points of D. That is what is meant by not dense. Not that for every x in R and for every R. No, that's not what it says. At least some place it is like the points of D are like mosquitoes in Bangalore. Okay, they are dense. Wherever you go and however small a mosquito net you put, there will be a mosquito inside. Right? So, if the malaria eradication department had done some work, some place in Bangalore may be there, maybe beyond Koramangala or wherever it is, where you can put a sufficiently small net so that you can avoid mosquitoes. That is what is meant by not dense. Okay. So, I am going to bring this because there is some other definition I am going to bring in, that is called nowhere dense. It should not be confused, these three must be very clear. So, dense means everywhere these mosquitoes are going to bother you. Not dense means at least in place you are free from the mosquitoes. Let us also look at another consequence of dense means. Okay. Suppose D is dense. What does this mean? If I now take a point X and draw any radius R, there will be a point D of D inside that. Now, if X is in D, there is no problem at all. The center is always there, however small you are going to write, already one mosquito is inside the net. Okay, you are unfortunately constructing your mosquito net around a mosquito. In fact, my friend used to have a very nice way of avoiding mosquitoes. Suggestion. If you have seen mosquitoes, somehow they will find a hole in the mosquito net and get it. So his idea was that create a hole in the mosquito net, one by one all the mosquitoes will get inside, seal the hole, come out and sleep. Okay, something like that we are trying to do, see whether we can do it. So now suppose, so I have got a D. So let us assume, for example, X is not in D. Suppose I take an element which is not in D, and now I construct a disc or a ball of radius 1, say, whatever it is, let us say radius 1. There will be an element of D inside that, and this D will be different from X, because now X is not in D and this element of D must therefore will not be sitting at the center. If it is not sitting at the center, then this distance must be positive. Call it as some R1. Okay. So now, let suppose D is dense, there exists a D in V1x, D not equal to X, obviously, because X is not in D. So let R1 be the distance between X and D, and this is strictly positive because X and D are different. Positive. Now you consider R1 dash to be rho XD by 3 or 2. Even 2 is enough. Let me make it easier. Okay, 2. Then what happens? I have got a disk. This is half of the distance between X and D. So D will lie outside that. So let me call it a D1. Okay. But now inside BR1 prime X, there must be an element of D, because again D is dense. So there exists D2 belonging to BR1 prime X, and D2 is not equal to D1. Now what is your guess? I am going to go on doing this. Okay. Now take another half of this radius and then you get one more point inside. So what do you get eventually? You get a sequence. What will happen to that sequence? the distance is reducing half of the previous time, and therefore it will go to 0. So if the distance is going to 0, that means it is converging to x. Okay, so let me not write all the steps. Continuing this process, we get a sequence of elements d1, d2, etc., dn, etc., belonging to D, such that the distance between x and dn is less than, is equal to half of the distance between, less than half of the distance between x and dn minus 1, because it is inside the circle of radius half of the previous circle. So therefore, every time it is getting halved, less than halved in fact, therefore the distance is going to go to 0, and hence rho x dn tends to 0 as n tends to infinity, and therefore dn tends to x. Therefore, every element which is different from, which is not in D, can be approximated by a sequence of elements in D which converge to D. Okay. So therefore, if x is not equal to D, if x is not in D, I will come to x belonging to, then there exists a sequence dn belonging to D such that dn converges to x in the metric space. Okay. What happens if x is in D? Sequence is a constant sequence, d, 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 d. So therefore, obviously this is true if x is in D. If x is equal to D, if x is in D, we can take the sequence dn equal to x for every n. So the final conclusion is, whether it is in D or not, every element of x, for every element of x, there is a sequence of D elements which converge to that. Okay, so if D is dense, so the conclusion is if D is dense in x row, then for every x in x, there exists a sequence dn in D such that dn converges to x in x. Okay. So that's one good property of the dense set. Everything is eventually therefore boiling down to looking at dn, the D set. Basically we can get a lot of information about the whole set. Now since I have written down this three aspects, I will, before proceeding further, I will introduce some more notions. Okay. What are the notions we introduce? Dense. In bracket, that means everywhere dense. Wherever you go and whichever ball you take, there is a point inside. That is dense. I will simply call it dense, but at the back of mind, think it is everywhere dense. Then we have looked at the negation of it. Not dense. Okay, that we have seen. That is, somewhere I wrote, no, not dense, here it is. Okay, a negation statement. Now you just simply use one more word, somewhere dense. What does somewhere dense means? Now the word everywhere suggests. Everywhere says whichever ball you take, there is a point in it. Somewhere means there is one ball where whatever inside you construct small balls, there will be a point. This means there exists a BRX such that D is dense in BRX. That is, every element in this ball can be approximated by a sequence of elements in Dn. I will put in terms of the language. That is, for every y in BRX and every r prime greater than 0 such that Br prime y is contained in BRX. That is, now universe is only BRX. We are completely ignoring the other parts, shutting down the other parts of the metric space and looking only at this smaller universe. So you take a small, this is the whole metric space. Inside that metric space there is a small universe such that now you take any point inside and any radius which lies in that universe, then then every r prime that the intersection Br prime y D is non-empty. Okay. The same thing as saying in terms of sequences, that is, for every y in BRX there exists a sequence Dn in D such that Dn converges to y. Okay. So in a small patch it is dense. Okay. Suppose you take all the rational numbers less than 1. Take all the rational numbers less than 1. Certainly it is not dense in R, because if you go to 46, you can't approximate by a rational number less than 1. But if you are looking at rational numbers, positive rational numbers between 0 and 1, then the rational numbers less than 1 will be dense there. So it is in a patch it is dense, but not all over the place. Okay. So in other words, some parts are affected, inflicted by these mosquitoes, but there may be large portion where it is not. But there is some portion which is completely affected by these D mosquitoes. You have called it M so that the mosquito will be there. Okay. So we have now dense, not dense, somewhere dense. So what is everywhere dense? Somewhere dense holds for all R and X. Okay, every somewhere is dense. Okay, when they say every which way you look. Okay, every somewhere you look, it is dense. Right? Yeah. Yes. With R dash chosen such that you are inside. Okay. Such that I have written R dash greater than 0 such that Br prime y is contained in that. The whole universe is that. Okay. Should I slightly modify that, but we will stick to that. Okay. At the moment, intuitively, this is a right definition. Okay. Now we have dense, not dense, somewhere dense. Now what is nowhere dense? Nowhere dense is the opposite of somewhere dense, not everywhere dense. See, I go and search in my office, somewhere in one of the drawers, I have 5 rupees. I am not broke. Okay, I am not broke if somewhere I have 5 bucks. Okay, what is meant by I am broke? That is, nowhere I can find 5 rupees. That is, it is not dense anywhere. That is, wherever you go, there will be one small ball inside which will be free from d element. So that's a very important notion. So nowhere see, logic people should think, what is somewhere dense? There exists an X. Okay? So nowhere dense will be for every ball. Okay, so for every Brx, there exists for every Bry prime. So now this will be, there exists Br prime y contained in Brx such that Br prime y intersection Brx is empty. So every small universe has a smaller universe which is free from mosquitoes. That is what is meant by nowhere dense. That is, finally the eradication department has done a good job. Whichever part of Bangalore you go, there is a small part where you can sit comfortably free from mosquitoes. Okay? That is, nowhere in Bangalore mosquitoes are going to bother you so seriously. Okay? So that is what is meant by nowhere dense. For wherever you go, there is a small portion which is free from these elements. That is called nowhere dense. There is a different way of defining nowhere dense, but I like this definition, this way of looking at it, because it tells exactly what is happening. Nowhere it is going to bother you. That means at any place you go, you can live freely without being bothered by it. There is at least one small room where you can sit without mosquitoes, a small public park probably, where you can freely sit without mosquitoes. So we have dense, that is everywhere dense, not dense, somewhere dense, nowhere dense. Okay. Yeah. Intersection, this one, what? Huh? Oh yeah. Good. That means you have understood the definition. Okay. See, sometimes you must deliberately make some mistakes so that you know whether this is being followed or not. By the way, I had a teacher who taught me analysis. I mean, he didn't teach me analysis. I met him once after classes all started with a master's program. I said, sir, I want to read some good textbooks. Then he said, what is the main interest? I said, I want to read analysis. So he gave me a book and then said, you read the first 10 pages during this week and you must come back and show me at least 15 mistakes in the book in the first 10 pages. And then I said, if there are so many mistakes, why are you giving me this book to read? Then he said, if you can find those mistakes, it means you have understood the subject. So it's better to read this book, and by correcting it, your sharpness increases. Now, I will be giving you only 15 in the beginning, but as you go along, I will expect more and more mistakes to be found out in this book. It's a very bad book, but it's a nice book to learn through mistakes. Okay. Sometimes mistakes are good. Okay. So like that, sometimes even knowingly or unknowingly making a mistake is good. Okay, so now we have these various concepts. At some stage, we will use this notion, nowhere dense. It's a very, very important notion. Well, probably I should make some comments here that namely, I keep on making this again and again, this something being small and big is context sensitive. So you can use language, the languages man's language, okay, the formal languages terminology. It is context sensitive. What is small in one context may be very big in another context. What is big in one context may be very small in some other context. That is, something may be said theoretically small, something may be said theoretically very big, but measure theoretically very small. Okay. An infinite set has measure 0. A countably infinite set can have measure 0, and even an uncountably infinite set can have measure 0. There are uncountably infinite sets which have measure 0. So, set wise it is very big, but measure wise it is very small. Like that, the smallness and bigness are context oriented. So, these no dense sets are in a sense meager sets topologically. They are very meager sets topologically, but it is not necessary that they are meager in some other context. Okay. So, in the context of metric spaces and topological spaces, these no dense sets are considered as meager sets, because you see you are able to avoid them. There is a lot of gap in those sets. Okay. So, now let us get back to dense sets, and let me give you a lot of examples now. Of course, all the examples will be in the standard metric spaces that we have seen. Okay. These are our role models. Okay. So, examples. Of dense sets. Now, if you take the real numbers, this is our starting point. Clearly, Q is a dense set. That is our starting point anyway. This is what motivated definition. Clearly, the rational numbers is a dense format, give us a dense set in the real numbers. And similarly, irrational numbers. The irrational numbers, because between any interval there will be an irrational point. The irrational numbers, I will call it I, also is a dense set. The set of is also a dense set. But if you take any finite set in the real numbers, it will certainly not be dense, because if you take a finite set just up and go sit farther away from him, then he is free from this set. So, no finite set can be dense. No finite set can be dense in R. So, you see, look at R as a vector space. As a vector space, and you are studying linear processes, then it is dimension 1 only, one vector will be enough to determine the whole space and everything works there. So, it is finite dimensional space. But if you are working in R, but not working with linearity and other structures, but you are working with continuity, then your sampling has to be done on a dense set, and it says you can't do it finitely. The topological continuity is a topological property. Okay, it involves limiting processes. When you do linear algebra, you do only finite. In R, there is only a finite linear combination that is needed. Everything can be written as finite linear combination. But when you are doing continuity, you are doing limiting processes. And in that case, if you are doing topology there, then it is no longer possible to have a finite sampling set. So, in the topological sense, the metric space sense, the sampling set cannot be finite, but has to be infinite. Infinity we know is countable infinity, it. Okay, you can't do it finite, but you can do it with this plus infinity that you can think of. So therefore, you see this R itself as a vector space as a finite sampling set, a finite basis, but as a metric space, if you are looking at it from the point of view of continuous processes and all, it requires a very large sampling set, and only advantage is, well, I know finite will not work, but the Q tells me that the smallest infinity will work. Okay, so therefore the smallest dense set in R must be countably. Okay. Let me put it that way. The any dense set, hence any dense set in R must be infinite, and Q gives us the smallest sized infinite dense set. Okay, that's countable. However, if you take the irrational numbers, that is also dense, but that's too large. So it's a very bad, it's not a very good sampling set. Then Q is by far the best. You can do a little better, but stick to Q. But still, countably infinite is necessary. That's our first example. Always first example is R. Then our next examples will be building from R. If you start with R and put two copies of R, you get the two-dimensional space. Okay, or what we call as R2. Okay, so now let me take the second example. So whenever you go to 2, we have to introduce a new metric. Okay, so we look at first L infinity to R. What is this metric space? It consists of vectors with two components, two real components, and the distance between two is maximum of x1 minus y1, x2 minus y2. Good. So therefore, now let us look at any vector in this space, any element of this metric space, and let us take any epsilon positive. We would like to find that set, we don't know which set it will be. I want to have a set D such that where should that set D lie? It should be in L infinity to R, that means it must lie two-dimensional vector collection, such that any x and for any epsilon, one fellow will come there and approximate it within epsilon. So we are trying to locate that. Right. Now x1 is in R, right, because the components of the vector are real numbers. Now the moment I have a real number, I can approximate it by a rational number. Implies there exists a rational number q1 in Q such that mod x1 minus q1 is less than epsilon. This is by example 1. Q is dense. Similarly, the second component is in R. Let us say that can also be approximated by a rational number within the error epsilon. Okay. So each component, remember when you are dealing with this R2, Rn with various metrics, we talked about convergence. It all boiled down to coordinate wise convergence. Like that, now we are trying to approximate. It is going to boil down to coordinate wise approximating. Okay. So the first coordinate can be approximated by a rational number. The second coordinate can be approximated by the rational number. Now we are going to construct the vector to be q1, q2, and therefore what is the distance between x and q? The maximum of x1 minus q1 and x2 minus q2, each one of them is less than epsilon, and therefore that will be less than epsilon. So what have we done? All we have done is given any vector in this space or any element in that space and given any error epsilon, we are able to find an element of this form. What is this form? Vectors, all the components are rational numbers. So what is the conclusion? So let D be equal to Q2. What is Q2? Q cross Q. Right? Then this gives, then we have for every x in X, L infinity to R, for every epsilon positive, there exists D in D such that rho infinity xd is less than epsilon. And therefore, D is dense in L infinity. So Q adjusted R. Now I got R2 by taking 2 copies of R. Then the adjustments also take 2 copies and okay. So Q R was here and it was approximated by Q. I took another copy. Well, okay, you take another copy and that is going to be approximated. Okay, so Q cross Q is dense in R2. What about L infinity 146 components? Will there be any change? Same thing. And therefore, if I now put n there, similarly, for any positive integer n, q power n is dense in L infinity with n components. Because each component is less than epsilon by a rational number, put all the components as the one vector and you got what you want. Okay. So you are just doing it component wise approximation. There is no real problem there. So R is, in R Q is dense, in L infinity n, Q power n is dense. These are important dense sets. Now what we will do is straight away go to this. Instead of L infinity on the n component vectors, I put the P metric. Now let us see what we will do. We will be very careful. Okay. So we are given x and we are given epsilon greater than 0. What should we do? Again we must look for a set from which I can approximate this fellow within that error epsilon. Okay. Same arguments we will do now. So we will now have to do a bit of adjustment. Take any other error which is convenient to us. We will adjust later what error we are going to adjust to. Take an arbitrary error, then x1 can be approximated by a, well, there exists a q1 in q such that mod x1 minus q1 is less than epsilon 1. And we can do this for everything. So for there exists qj belonging to q such that mod xj minus qj is less than epsilon 1. and therefore some, let Q be this vector Q1. Okay, let me not write that first. What about summation j equal to 1 to n mod xj minus qj to the power of p less than n epsilon 1 to the power of p, right? Or summation j equal to 1 to n mod xj minus qj to the power of p to the power of 1 over p is less than n to the power of 1 over p epsilon 1. Okay, so therefore I want this to be less than epsilon. So how do I choose epsilon 1? Epsilon by n. Okay, so given epsilon positive, choose epsilon 1 is to be epsilon by n to the power of 1 over p, then we get q1, q2, qn such that summation j equal to 1 to n mod xj minus qj to the power of p to the power of 1 over p is less than epsilon. So that is, if we let q equal to q1 qn, then rho p xq is less than, but this is in. So once again, given any vector and any error, we are able to approximate it by a vector in q power n with the within the error epsilon. So therefore q power n is dense in L, P, N, R. Okay, so we move on now one step apart. From real, we put 2 copies of the real, then we put n copies of the real. You take any one of those standard metrics, p matrix, p can be 1 to infinity or even infinity as in the previous example. Always q to the power of n is a dense set. Okay, so conclusion therefore is this is dense in this for all values of p including infinity. Infinity was the previous example. Now we have done other p's. So for all such p's, q to the power of n works as a dense set in these LP spaces. What is the next level we raise the bar to? Now go to sequence, put more components, put infinite number of components. So now we will be doing it very carefully. What is that example number? N plus 1 or n, okay, example 4. So let us first consider this. We will look at 1 less than will be less than infinity. We will look at the L infinity case later. Okay, we will make some other comments about it. So now what does that mean? And we look at LPR. Now I don't have to put n because the number of components is increasing. So LP infinity. So if x is in LP, what does that mean? X must be x1, x2, xk, etc. such that summation j equal to 1 to infinity mod xj to the power of p is less than infinity. We consider all those vectors for which this series converges. Alright, so we are going to look at such vectors, and suppose now we are given such a vector and we are given epsilon greater than 0. Now suppose I try to follow the earlier proof. what will I get? For Q1, for X1 I will get a Q1, for X2 I will get a Q2, for each one of these I will get a Q, but then what will happen here? This will be infinite sum and each one is epsilon 1 to the power of p, but then if I try to add infinite epsilon 1s I may get infinity. So there is a breakdown, because this proof cannot be copied, because if you put too many small things it may become big. So therefore that proof fails. It does not mean that we abandon that. What we should therefore do is somehow bring it to the problem of finite sum. Somehow bring it to the problem of finite sum. The way we do it is the following. First thing we look at is, this series is finite, this series converges. If a series is convergent, the tail is very small. So you can approximate the tail by 0 coefficients. All components as 0, and only the head you will have to approximate by the rational number. So the idea therefore is the following. First chop off the tail. Given, since the series, since summation j equal to 1 to infinity mod xj to the power of p is less than infinity, for any epsilon 1 positive, again I will adjust epsilon 1 later, we can find an n1 such that if we now look at the series after the n plus 1th term, that can be made less than epsilon. Because the series is convergent, the tail can be made small by sufficiently far away if you take the tail. That is the idea of a convergent series. So that's one. So I already made the tail part small, we don't have to worry, you can take all the qj's to be 0 there. Okay. So now we'll worry about it later. Therefore, now look at x1, x2, xn1 and get q1, q2, qn1. Now you are back to this problem. I have a finite number of components, I can get a finite number of this thing such that summation, what happened to the board? Summation mod xj minus qj to the power of p, j equal to 1 to n1 to the power of 1 over p is less than epsilon 1. Right? Once you are in finite case, you can do that. Okay. Look at only the head part of the sequence. The head part is in LPN N1. Okay, so now what do I get? Now what I do is, I set Q equal to Q1, Q2, Qn1, all these Q's that I got, and then the remaining things as 0. Right? Is that in LPN? LPR? Because there are only finite number of components, the sum of the pth power will definitely be finite. So that is in LPR, no problem. And what is rho p x q? Let us look at the pth power of this. Okay, that is summation j equal to 1 to infinity mod xj minus qj to the power of p. Now I will split it into two parts. In the latter part, what is qj in these places? It is 0, so it is only mod xj to the power of p. Now what do I know about this? This is less than epsilon 1 to the power of p. Because of this, this is 2, and that is, where is that? Say that? What is your problem? Here, look at what I have written. In the previous case, eventually I can make the whole thing a smaller. Okay, that I already combined and I got this. So that is less than epsilon 1, and probably this will also I will make it p. Okay, so this is epsilon 1 to the power of p, that is 1. So therefore, rho p x cube is less than 2 epsilon 1 to the power of p, is less than 2 epsilon 1 to the power of p, or rho, what happened to the board? Rho x cube is less than 2 to the power of 1 over p epsilon 1. So now what do I do? If epsilon is given, I choose epsilon 1 to be epsilon by 2 to the power of, choose epsilon to be epsilon 1 to be epsilon by 2 to the power of 1 over p, and we have rho p x cube is less than epsilon. Right, what have we done so far? Given any vector or given any element x of that LP space and given any epsilon positive, I am able to cook up a very peculiar cube which approximated with less than epsilon. What is that peculiar minimal cube? It has all but a finite number of components as 0, and these non-zero components are all rational numbers. So let us denote by, let q hat be the set of all rational sequences all but a finite number of whose terms are 0. Okay, and q is one such animal. So therefore, given any x, given any epsilon, I am able to get a q from this which approximates x within epsilon. Okay, so therefore, for every x, for every such x, there exists a q in q hat such that rho p x q is less than epsilon. Therefore, q hat is dense in, I am sorry, in LPR. Okay, is that clear? So now let us consolidate all the examples we have got. In the R case, we got one dense set which was q. Q is countably infinite. In all the LPn cases, we got q power n. If q is countably infinite, q power n is also countably infinite. So there also we got a dense set which is countably infinite. Then we came to LPR. Again we got q hat. Q hat is also countably infinite. Why is q hat countably infinite? First take all those which have only one component non-zero. That is essentially q, countably infinite. Then two components, that is essentially q squared. So these two again is countably infinite. Q cube is again countably infinite. So it is the union of all q power n's, and each q power n is countably infinite, and therefore it is countably infinite. So here again we got a countably infinite dense set. So in all these examples we got countably infinite dense sets. So therefore we are tempted to make a conjecture that every metric space will have a countably infinite dense subset. right? So in other words, you take, but we have taken now how many readings? R, L2, L3, L4, L5, L6, L7, L8, etc. with P equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have done infinite number of experiments. In all these cases, this statement is true. So this being the centenary year of Turing, probably the Turing machine will halt and give us the output that all metric spaces have countably infinite dense subsets. Now we look at an example. First, probably important example of a metric space which does not have a countably infinite dense subset. Now look at this. In this example, I put equal to infinity. Now I look at L infinity. Okay, that example. Okay, I'll just make that statement first, and then I will probably indicate the why it is so. This is a very important example because this is the first major example of a non-separable matrix. So the example 5. I will show only this. Any dense set in L infinity R must be uncountably infinite. Therefore, it's useless. It's too big. Sampling is terrible there. Okay. So this is the first example where we get to see that there could be metric spaces which do not have good sampling sets, and therefore we separate these two, the good ones and the bad ones, and we give a definition. A metric space is said to be separable if it has a nice sampling set, that is a countable dense subset. Of course, if it's finite, wonderful. At worst, countably infinite. So we combine finite and countably infinite in one word, countable. So definition, this is why we make this distinction. Definition: a metric space X row is said to be separable if it has a countable dense subset. All the examples we have seen so far are separable spaces. The first is the non-separable space because it cannot have a countability. So this is non-separable. All the other previous examples of separable matrix. Okay. Nice things can be done in separable matrix spaces. We will see why that separability is important. Even with separable, there are many things that we cannot do. Okay. Okay. Let me indicate why L infinity is not separable. It is the L infinity, it first suggested that we have to distinguish the two cases, those metric spaces which have countable dense subsets and those metric spaces which do not have countable densities. Okay. Why is L infinity not separable? So let us look at example 5. And ask reason. Any dense set in L infinity must be uncountably infinite. Claim. Why is that true? I will just briefly indicate the proof. Now look at first the set K of all binary sequences. What are they? K is all such vectors such that xj are either 0 or 1. Look at all those vectors whose components are either 0 or 1, right? They are obviously in L infinity. What does L infinity consist of? All bounded sequences. This is obviously bounded, either 0 or 1. So this is bounded sequences. Okay. So therefore, this set is definitely contained in L infinity R. That is the first observation we will make. Set K of all binary sequence is a subset of L infinity. How big is it? Yeah? As big as real numbers, because any binary sequence is associated with the real number between 0 and 1. So it is as big as the interval 0, 1, and the interval 0 is as big as the real numbers. Okay? So clearly, these words are dangerous. Okay? Clearly, K is equivalent to the interval 0, 1, which is equivalent to R, and therefore K is uncountably infinite. That's so think about binary sequences, which is a subset of the sequence of bounded, the collection of bounded sequences L infinity, is an uncountably infinite subset of L infinity. Now suppose I take K1 and K2 in K, two different elements. Suppose I take two different binary sequences, two distinct binary sequences. What will be the distance? Because at least one coordinate will be different. So if that fellow is 0, this fellow is 1. If this fellow is 0, that fellow is 1. So the difference will be 1, and therefore the maximum difference will be 1, because maximum difference can be either 0 or 1. So therefore the distance, notice this very important property, these elements are sitting at a distance of 1 from each other. Okay. Any two of them are sitting in a distance of 1 from each other. Now try to even think of points in three-dimensional space which are sitting at distances of unit distances of each other. Can you think of three such points in the plane who are sitting at a distance of 1 from each other? Yeah? Can you think of 3 points in the plane which are sitting at a distance of 1 from each other? Take a length of 2 inches, take the midpoint. Is it true? No, because those two fellows are going. So therefore, if I put anywhere in between, it is gone. 2 points have to be in a line, and these two have to be 1. So that's fixed. 2 points A and B I can find within distance of exactly 1. But I am trying to locate the third point. If I put it here, it is gone. If I put it here, it's gone. If I put it here, what happens? This has to be 1 and that has to be 1. Is it possible? In a triangle, the sum of the sides, lengths of any two sides must be greater than the third side. So that's also not possible. So it's even so difficult to locate points like this. But in L infinity, look, there are so many of them. Yeah, this is, I'm sorry, this is what is known as the equilateral triangle. What happens fourth point? Yeah, this is what I have. What about the fourth point in 3 dimension? Even to go to the fourth point, you have problem. But if you go to three dimensions, it's possible. The tetrahedron can. Now you try to get 5 points in the third dimension. It's not possible. So there is such an amount of restriction of finding the points. You can find at most 2 points along a line, 3 points in a plane, 4 points in the 3 dimensions, and so on and so forth. But however, when you come to L infinity, you are able to find uncountably infinite number of points which are sitting at a distance of 1 from each other. That's very amazing. Okay, but this is a big problem to locate that the points sitting at a distance of 1 from each other. It's of itself a big problem in Banach spaces and all. So we will not get into that. Okay, so you will get 3 in R2, 2 in R1, 4 in R3. Conjecture, see whether it is n plus 1 in n. That itself is not an easy problem. Okay, right. Okay, now what does this mean? Suppose I take K1 and K2, 2 different points, right? And then consider the ball of radius 1 by 3. Will they intersect? Because the distance is 1, they will not intersect with each other. Okay? So these balls are intersect with what? They will intersect with L infinity. But the only point of K that will be in this will be K1. The only point of K that will be in this will be K2. Okay? So for each K in K, B 1/3 K intersection K is K itself. The only point of K in that sphere will be the center. Any other point will be not in K, because the distance from another fellow is at least 1 distance away. You are allowed only 1/3 distance in this ball. So how many such balls I got then? If I now construct for each K, I construct 1/3 radius, then I will have uncountably such balls. Now, in each such ball, suppose I had a dense set, there must be a point of D. Okay, if D is dense, if D is a dense set, in each B 1/3 K, there exists a QK belonging to D. Right? Because D is dense. Now, if I take 2 different balls, the same QK cannot appear in 2 different balls because they don't intersect. Okay, so therefore, K1 not equal to K2 implies QK1 not equal to QK2. In fact, I should write there, don't intersect at all. Doesn't matter. So now what happens? Corresponding to every K, I get a unique point of D. So now define a map F from K to D as F of K is equal to QK. Is this a 1-1 map? K1 is not equal to K2, Fk1 is not equal to Fk2. F is 1-1. So if you have a 1-1 map, then that means the size of K is less than or equal to size of, or the size of D is greater than or equal to, everything in K can be packed in D. So therefore the size of D is greater than or equal to K. K is already uncountably infinite, and therefore D must be uncountably, implies D is uncountably infinite. So therefore if you have a dense set, it must be uncountably infinite. So L infinity cannot have a countably dense subset. So that is the one that suggests you have to now categorize metric spaces as those which have countably dense sets and those which do not have countably dense sets, and that gives us the notion of separable metric spaces. So all the examples of the LP type seen, they are all separable except this L infinity R. All others are separable metric spaces. Okay, this has something to do with the functionals that we will study later, but hopefully we will study later. Okay, so I will stop here. In the next class, what I will do is I will give you one or two more important examples of separable and non-separable metric spaces, and then basically introduce the notion of continuity and see how the separability, at least the dense set, help you to capture continuous functions, get a good sampling set for continuous functions. So then we would have two basic concepts, completeness and separability. And I will introduce one more basic concept, namely compactness. This is a very fundamental concept, okay? And probably that will be the basic groundwork for doing functional analysis. Okay? These are the types of sets that you will have to deal with when you are doing functional analysis. So what I will do is some examples of separable and non-separable still, then I will possibly introduce continuity, then compactness, then this idea of nowhere dense sets, and a fundamental theorem called the Bayer's category theorem, which gives many things. The Bayer's category theorem is the root of many theorems in analysis. Okay. So we will look at the Bayer's category. Once we have this, we will move to nonlinear spaces, where real functional analysis starts. Okay. We are still about to start, not yet started.